Welcome to Frontline Systems webinar on an overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am Consulting Lead and Modeling Specialist at Frontline Solvers. During the presentation, if you have any questions or comments, please type them into the chat box to be answered at the end as time allows. I strive to remain within the promised 30 to 45 minutes, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the optimization applications are widely used across many industries and functional areas. We would like you to know that many of our customers have found optimal solutions for their industrial problems worth millions in savings, as building a model can give you insights and a money-saving optimal solution. Today, we explore how optimization can benefit you in solving your business problems and how easy it is to use our tools to solve them. Together, we'll review typical applications in transportation, inventory management, financial services, scheduling staff, and one example of automating optimization using VBA. Maybe you wonder what solvers are good for. So let's start talking about the decision-making process and using optimization to solve a problem. It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be money, equipment, staff time, transportation fleet, raw material inventory, for example. All of these are resources and they are allocated for some purpose, deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. Portfolio optimization is allocating money to stocks in a portfolio, and scheduling is really a matter of allocating people to time slots or scheduling the availability of hospital operating rooms. Solvers or optimizers are software tools that help you determine the best way to allocate those resources. And now you might be wondering what you need to do to use a solver or how to define your optimization model. Let's drill down on this further. As you can see, there are three main steps. Each optimization problem involves one or more decisions that must be made in order to solve the problem. The decision variables are typically numbers reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. These decisions need to be made in best possible way while simultaneously satisfying a number of logical constraints or conditions. Constraints reflect the physical situations, and there are various types of these constraints. Some of them represent limits on available resources such as inventory or money. And there are constraints that reflect the physical situation. One of them is like non-negativity on variables. You cannot produce a negative number of products. You cannot assign a negative number of people to tasks. And some constraints are determined by policies that you or your organization may set. For example, in a portfolio optimization, you might have a limit on the maximum percentage of funds to be invested in any one stock or one industry group. Then you might also have balance constraints. For example, warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in. And these type of constraints usually have an equality form, and we will look at some examples. Another common element in each optimization problem is the existence of some goal or objective that the decision maker considers when deciding which course of action is best. You can determine the objective function by asking what measures are we trying to optimize. The best or optimal solution might mean maximizing profits, minimizing costs, or achieving the best possible quality. Now, let's dive in and see how we can solve a problem in practice. Transportation and logistic operations of your company can be a competitive differentiator. So let's find out in this example how optimization can be used to optimize a transportation operation. This company has 3 different goods that have to be shipped from 2 factories to 4 warehouses, and from those warehouses to the 5 customers, or directly from factories to the customers with minimum cost. Here's a diagram of the system, and it has notes for factories, warehouses, and customers. Now, we need to show the supply-demand pairs displaying feasible routes for the shipment plan. These gold car arrows show the potential flows from factories to warehouses and customers, and then these green arrows show the potential flows from warehouses to customers. Now let's take a look at the Excel workbook, which is ready for us. This is the full analytic solver platform ribbon, which includes optimization, simulation, and data mining. Today we are going to focus on a subset of ASP called Premium Solver Platform, so we can change the product. When you are using a free trial of our software, you can also do this yourself. So let me show you how. Click on Help, Change Product, and here instead of Analytic Solver Platform, let's choose Premium Solver Platform. Now click OK. Now we only have access to the optimization. Let me adjust this size. Okay. So let's just skim through the Premium Solver Platform ribbon together. As you can see, clicking on the Model tab displays or hides the task pane. In the Model drop-down, there are additional options for multi-dimensional modeling that are beyond the scope here. Then, in the Optimization Model tab, you can set up optimization models, including decisions, constraints, and objective, which we will practice later today. Parameter tab provides the options for you to run multiple parameterized optimization. Solve Action tab allows you to solve optimization models. Here on the Analysis tab, you can analyze the results, create different reports, and charts. Tools tab enables you to examine optimization results. The Publish button allows you to publish your models for use and distribution on the web. This allows you to help to use these models in using our Solver app that is available for Excel Online and Google Sheets. Now let's explore the Help tab. Here you can display online help, use live chat, control guided mode, which we will discuss in more detail today, open examples or an online tutorial, access user and reference guides, and check your license status and more. So now, we saw that this Model tab displays or hides the task pane. So let's check the task pane together. So this Model tab, as you can see, allows you to view the model in outline form. You can see the results of model diagnosis and optionally edit model elements in place. Next is Platform tab. Here you can view or change the platform options, such as the number of optimizations to run or the default bounds on decisions or uncertain variables. Then we have the Engine tab. Here you can select the Solver engine and then set its options. And finally, the Output tab allows you to view a log of solution messages or a chart of the objective value. So let's go back to our example. As you can see in this Excel workbook, the cost of shipping from factories to warehouses, factories to customers directly, and from warehouses to customers are recorded in these cells. These are inputs to the problem that are not under our control. These shipping costs are quoted to us by our outside shipping company, for example. But what is under our control our decisions about how much to ship along each route at these different locations. So we need to reserve cells for variables representing quantity shipped from factories to warehouses, from factories to customers directly, and then from warehouses to customers. This is how we define decision variables. And then, as you can see here in the Model tab of Task Pane, 3 sets of decision variables are defined. Now, what measure are we trying to optimize? Each route of flow incurs a cost. There are 2 goals that need to be carefully addressed in this problem: the total costs and service. We want to provide the service with minimum cost and ensure that each customer demand is completely satisfied. So the objective function is minimization of total cost of shipment along all the routes. So here is our objective function: total cost of shipping in cell C91. It is represented by a sum product function. So, for example, the first component, to calculate total cost of shipping from factories to warehouses, since the cost coefficient for these routes are defined in cell C10 through F15, we need to multiply these by total amount of product that will be determined to be shipped, our decision variables, for which we have reserved cell C41 through F46. And similarly, we need to add the other costs. So this is defined as total cost cell. Now on to constraints. What restrictions limit our choice of decision variables? The capacity of each warehouse, supplies available from each factory, and the demand from each customer need to be considered. Here are warehouse capacity constraints. We want to make sure that what we ship into warehouses doesn't exceed the capacity of those warehouses. We cannot overload warehouses as each one has a physical capacity. We have a certain supply available at each factory provided in cells H63 through H68. The total flow out of factory 1 for each product type must be smaller than or equal to the factory supply. This is the same for factory 2. And we have these constraints for factories. Then we need to ensure that each customer product demand is satisfied. So here are these constraints: total to customers greater than demand. And then warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in. These types of constraints are called balance constraints, and they have an equality form, as you can see. Now, let's go ahead and solve the model by clicking the Optimize button on the ribbon. This time, we are going to step our way through guided mode and see what it can tell us. This feature is a guide offering help for you in each step of your modeling efforts, preventing common errors. Now let me click on Continue. 2 things happen here. First, Solver has analyzed all the formulas in the model and determined the structure of our model, which is LP convex. But because the right solvent engine wasn't selected, it is letting us know and giving us other choices. So I'm going to choose the right engine, which is a standard LP quadratic that is offered, and then click on Next Step. Now guided mode tells us that Solver found a solution, all constraints and optimality conditions are satisfied. So let's click on OK. And now we are back to where we were, without the guided mode. Here's the solution. We achieved what we wanted here, which was to determine how best to ship products between the factories, warehouses, and customers. And so to minimize our shipping cost, which is now $519,700. quick note, after you have used guided mode for a while and you're solving over and over, you might want to get rid of these dialogues that you have to click through every time. To make this change, click on Help and then click on Operating Mode. Instead of going to Expert Mode, which is the third option, and eliminates the help, you have another choice, Auto Help Mode, which will only bring up the dialogues when there is a problem. And we usually recommend you to use Auto Help Mode if you don't want to use the guided mode. But let's keep the guided mode for this practice. So, we just looked at how optimization can help us with a typical transportation problem. Next, let's look at an inventory management example. Let me open the workbook. A warehouse sells 4 products with a different demand for each product. Each product has a different holding cost and requires a certain amount of space. We have a limited storage capacity. So, what is the best ordering policy for a warehouse to minimize cost while meeting demands? As you might know, there is an analytical solution for this problem, which is known as economic order quantity, or EOQ. Unfortunately, this formula doesn't always work in real world. Demand usually fluctuates, order time is variable, and other factors arise to further complicate the problem. In this model, we have one such factor, a limited storage or space. The variables are the amount to order each month for each product. We call them quantities, and they are defined in cells B13 through B16. By changing these variables, we change the total costs. So we have one constraint. A total space used should be less than or equal to our available space. And then let's look at the objective, which is the total cost. If we look at each component, it is the sum of these cells, and if I look at one, you can see that it is calculated by holding cost time average inventory level plus the cost to place an order times average number of orders. So this is a nonlinear problem. Let's hit the solve button and let's click on continue. It tells us that our model is nonlinear programming non-convex. Let's click on next step, and here we get the results. So we get the amounts to order each month, minimizing cost, meeting demand, and without exceeding storage space. Now, let's look at one example in a financial services application. This is about allocating money to stocks. An investor wants to target a specific rate of return for his portfolio while minimizing risk. This is a portfolio optimization application. So, the goal is to find the best combination of stocks that minimizes risk for a given return. The return, variances, and covariances between all stocks are known. In order to save time, I've already organized the data and have everything ready and added the formulas on the spreadsheet. But we would define the optimization model together. In this problem, the variables are the percentage allocations of funds that we can invest in each stock. So let's define the decision variables using the ribbon together. We can reserve cells C14 through G14 to hold the percentage allocations of the funds or the decision variables. So let's select these cells and then click on Decisions to define them as normal decision variables. And you can see in the Model tab that allocations, which I named these cells allocations, are now added as our decision variables. Now let's define the objective, the portfolio variance. I have defined a quadratic function at cell C18. using a custom quad product function. So let's select the cell, then click on Objective and choose Minimize to define C18 as a normal objective to be minimized. And again, you can see in the Model tab that this objective is added. And we have two constraints for this problem. The first constraint is the total portfolio constraint, summing the allocations of funds to stock, which is summing to 100% or 1. So we need to set up one cell in the spreadsheet to represent the formulas of this constraint. Here I use this cell, H14, sum of all allocations. Now let's use the mouse to select this cell and then click on Constraint and then choose Equality. On the right hand side, let's enter 1 or 100%. And H14 or total portfolio is our left hand side. Let's click OK, and this constraint is now added to our Model tab of task pane. Our next constraint is total portfolio return, which is a sum product of allocations and stock returns. And we want to make sure it is greater than 9.5%. So we need to set up one cell in a spreadsheet to represent the formula of this constraint. Here I have used cell C20. As you can see, I use the sum product function. Okay, use your mouse, select this cell on the worksheet, then click the constraint button. And let's choose constraints. This time, let's choose greater than or equal to sign. Now, portfolio return is our left-hand side, and let's enter 9.5% for our right-hand side and click OK. Now we can hit the Solve or Optimize button and get the results. Let's skip the guidance, and here are results, and you can see you can get a report of the solution on the Output tab. These allocations of funds to stocks, to different stocks, results in minimum risk or minimum variance portfolio and achieves 9.5% return. This is often called an efficient portfolio. You may have heard of efficient frontier. Using Premium Solver, we can construct that efficient frontier rather easily. And let me show you how right now. Go back to Model tab. Okay. This is this part we want to talk about parameterized optimization. So far in our example, we have used the solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Let's generalize that. We can utilize parametric optimization to find the efficient frontier that is the optimal solution for several levels of portfolio return. To do this, let's choose one empty cell. For example, let's choose D20. Now, let's click on Parameters and then Optimization to insert a parameter. This dialog box will open. We can input 8% for our lower level and 14% for our upper level, as one of our stocks returns 14%. Now, let's click OK. We can see that this parameter is added, D20, excuse me. Now, we have to go to that constraint that we have and set the number of optimization. We have to do two things actually. First, we have to go to modify the constraint right-hand side to point to our parametric return rate. So let's choose the portfolio return. Instead of 9.5%, let's select this and point to the parameter D20 and click OK. Next thing we need to do is to go to Platform tab and set the number of optimization instead of 1 to 10. Let me clear the output report. Let's click on Optimize. I will skip the guidance 10 optimization finished. This worksheet will initially display values for the last optimization, optimization number 10. But we can display any of optimization results by changing the selection in this optimization number on the ribbon. So I can choose optimization 1, optimization 4, or so on. Now we can click on charts, multiple optimizations, monitored cells. Let's select the objective portfolio variance. Click on this to select it and click OK. This is the efficient frontier plot. Now I can click on this button to open the right pane. And then let's click on chart options. Here for the X coordinate, instead of optimization index, I can choose the psi-opt-param. Now instead of optimization parameter on the X-axis, you can see the return threshold for each optimization. Let's close this. Go back to our slides. And now a recap on what we practiced: modeling and solving problems in Excel spreadsheets. You need to reserve a cell to hold the value of each decision variable. You can pick a cell to represent the objective function and enter a formula that calculates the objective function value in this cell. You can pick other cells and use them to enter the formulas that calculate the left-hand side of the constraints. The constraint right-hand side can be entered as numbers in other cells or entered directly in the solver's add constraint dialog as we practice. And one quick note, it is best practice to use constants for constraints right-hand sides. Now let's look at some scheduling examples. These examples are about allocating staff. Let me open the workbook. An amusement park needs a certain number of employees each day of the week. Every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire, and what schedule should they be on to minimize total payroll costs? So, for employees working 5 consecutive days with 2 days off, we are looking to find the schedule which meets the demand from attendance levels while minimizing payroll costs. As you can see here, we have 7 possible schedules. Decision variables, you can see here, cells D7 through D13, reflect the number of people hired for each of the 7 possible schedules. And you can see that they are defined as integer. The logical constraint. So we have to make sure the employees per day are greater than or equal to required employees. So we're satisfying the demand. And then our objective is minimization of payroll costs. And if you look at the formula, it's just calculating the schedules times the the payroll per day costs. Now let's click on Optimize. I will skip the guidance, and here are the results. The number of required people for each schedule. Now let's click on Schedule 2. This is the next example. And it is another version of this problem. The same park, as you can see here on the top, has hired the required employees. And now they need to decide which employee goes on which schedule. You can see down here that each employee has given a list with his or her preferences. A 7 means the most desired schedule and a 1 means the least desired. how should the park divide the schedules among the employees? Let me click on Model tab. Schedules are our decision variables. Each employee can be allocated to one of the schedules, either 1 or 0. And then you can see they are defined as binary. And we have defined this sum, the total, over all the schedules per employee, and we want to make sure that they're equal to 1. So just one schedule per employee. Then we have another constraint, employee schedules is equal to employee required. And they're just sum over each schedule. Let's look at the objective, total preferences, and we are trying to maximize the total preferences. Let me show you that this is a sum of all preferences, and if we look at one of these preferences, it's just a sum product of schedule assigned to that employee and then times its preferences. So in this model, we solve the problem after finding the optimal solution of previous example, which was the schedule 1. It is possible for you to find both solutions automatically, and you can write a VBA macro to do this. So let me click on Optimize. Let's skip the guidance, and here are the results. Now actually it's a good time to talk about automating your models. Automating your models allows you to run your predefined solver models and control the solver. You can automatically update data, run the model, and retrieve the results, and also create an application to distribute to end users. You can automate your models and control solver engines using VBA Object-Oriented API. So let's look at one example which is available for you to review later too. This is a refinery example. The goal is to plan the operations of refinery to maximize the total profit. This oil refinery purchases 2 crude oils, crude 1 and crude 2. These crude oils are put through 4 processes: distillation, reforming, cracking, and blending to produce petrols and fuels which are then sold. The VBA code for this model shows some of the many ways you can use the object-oriented API, such as how to call the solver and how to retrieve sensitivity information from VBA. So let's click on the developer and then Visual Basic to take a look at the code. With dim problem as new problem, we create an instance of the problem. I'm going to skip all the details, but here we select the solver engine in this line, and then we set its parameters. With problem.solver.optimize, you run the optimization. In the next line, we are going to put a message box, and you will see it as we run it. Then below is another a for loop. Within that, there's another message box here. And then we have the problem.solver.report, and we are asking for an answer report in this example. And you're going to see that what would happen as we run the model. So let's close this VBA code. And again, in the Model tab, you could see all the components of this model: variables, constraints, and objective function. So let's click on the VBA, the Run Model button. First, we get the decision variable values in the message boxes. Let's quickly pass through them. And then you start to see the reduced cost, the dual values, shadow prices, and it's finished now. And you can see the answer report is generated for us. Let's go back to our slides. You can access our optimization software within Analytics Solver platform or Risk Solver platform, or get it as a standalone program such as Premium Solver platform or Premium Solver Pro. Everything that we saw today can be done using Premium Solver Pro or more advanced products, subject to your model size. The Solver upgrade products have a very nice usability features with limits related to problem size, structures, and solver engines. The platform products allow you to add 8 different larger scale plugin solver engines that you can use to extend the power of these products. It makes it practical for you to solve very large problems essentially only limited by memory. But you can do much more with our products. We offer a complete solution for any type of conventional and stochastic optimization problems, simulation and risk analysis, decision trees, forecasting and data mining, and text mining. You can find optimal solutions for models with uncertainty using chance constraints, recurse decision variables, and robust optimization and stochastic programming methods. Our wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web, server, and desktop applications in any scale. As we mentioned earlier, many of our customers have found optimal solutions for their industrial problems worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline Solvers offers powerful tools to help you get a better solution by automatically diagnosing model structure, fixing problems for you, selecting the solver engine, and providing updated information at each step. Today we just explored one of these features, the guided mode that helped us choose the right engine. Okay, now you might be asking, what is the next best step to begin? If you haven't, please register at our website for free. Registration allows you to access our downloadable user guides, more than 40 example models like the ones we have been showing here today. Furthermore, it allows you to download a free trial at any time whenever you are ready if you haven't downloaded yet. Try it yourself. After installation, go to the example models by clicking on Help Examples. During this trial period, you have full technical support. You can ask questions, just give us a call, use live chat, or send an email. Thank you very much. Now it is time for Q&A. And I just have a quick announcement. We have a simulation webinar starting at 11 a.m. And if you are interested to attend, welcome. The link is, let me send you the link. And in this webinar, we explore simulation optimization, simulation applications using Risk Solver platform. If you have any questions, feel free to type them in the chat box. If you want, you can raise your hand. I can unmute you. You can speak up if you would like. And if you come up with questions later, feel free to contact me at consulting@solver.com. Again, the webinar on simulation is at 11 a.m. Pacific time. Within like 1 hour, 15 minutes almost. And if you're interested, just let us know right now. And we will send you the link, the invitation. I really enjoyed presenting this webinar to you, and I trust it was helpful to you. I look forward to future webinars with you. Just remember, you're welcome to send any questions